And we've got one more for you, if I may, something now known as a try. So it turns out that a try is even cooler, if you like this kind of thing, in that it does not devolve into big O of n. It is truly constant time. But there's going to be a price. There's going to be a gotcha. A try is sort of a fancier tree. And it's short for retrieval, but pronounced try for weird historical reasons. But a try is a tree, each of whose nodes is an array. Right? So this is all like crazy mashups now. People started inventing data structures just by combining different ones. So unfortunately, a lot of the good ideas are taken. But you just have benefits from certain aspects of those data structures. And combining them ideally gives you the best of both worlds, so to speak. So here might be the root of a try. It's literally a big node, a big rectangle. But it's actually an array. So there's like 26 locations in this picture here. And here's how you use a try, for instance, to store names just like the hash table. You treat each of the elements of that array in that node as like a letter of the alphabet, so A through Z, or 0 through 25. And if you want to store someone's name in here, you do so as follows. If you want to store like an H, you index into the H location. And if you want to store the second letter of someone's name, like an A, well, you add another node below it. And such one is connected to the other. And you then identify the A in that array. And then you go on and maybe put a G, if the goal is to store, spoiler now, Hagrid in this data structure. And then the R and the I and then the D. But when you get to the D, the end of the name, you have to somehow flag that this is the end of a name that we've embedded into this data structure. So whereas all of these are called out in white just to make obvious what we're connecting to what, green has to be like a bool that's true, that just indicates like the buck stops here. Like D is the last letter in someone's actual name. And what's kind of cool now about a try is that we can repeat this for other names as well. So for instance, here's where we might put Harry as well. And notice they share a common prefix, HA for Hagrid, HA for Harry. So we're reusing some of these nodes, some of these arrays. We can even slip Hermione in here too, borrowing only the H. But she gets the H, then the E, then R, R-M-I-O-N-E, and so forth. And we mark at the end of her name too that she's in there. Now, what's the takeaway here? Well, what is the running time of a try? How many steps does it take to find someone in this data structure? And let me zoom out so that it sort of suddenly becomes a massive data structure with even more in it. Maybe it looks, sorry. No, I'll keep it on this one. Maybe it looks a little something like this with just these three names. But how many steps does it take to find Hagrid or Harry or Hermione? No matter how many names are in this data structure. There's 3 at the moment, but it takes what? H-A-G-R-I-D. So 6 steps to find Hagrid. H-A-R-R-Y. 5 steps to find Harry. H-E-R-M-I-O-N-E. 8 steps to find Hermione. But notice that those steps are only dependent on what? The lengths of the humans' names. And let's assume that no one's going to have a infinitely long name. It's going to max out at what, like 8, maybe 18, maybe 20, 30. There's actually some pretty long human names out there. But it's going to be finite. You know it's bounded, whereas most contexts, n could grow forever. So what's compelling here is if you assume that the longest name is, I don't know, 50 for the sake of a theme here, then you know that finding anyone in this data structure will take you no more than 50 steps. 50 is thus a constant, which means you have big O of 1 running time. It doesn't matter if there's 1 million people in this phone book or 1 billion people in this phone book. That's going to definitely add more nodes to it, but it's still going to take you H-A-G-R-I-D, 6 steps to find Hagrid, H-A-R-R-Y, 5 steps to find Harry, even if there's 1 billion other people in that data structure. So now we actually do seem to have constant time if you assume that there's going to be a bound on the length of the name. Why don't we use tries for everything then? What's the price we're paying for this data structure, even though we've represented just 3 characters here? Yeah? It's a lot of memory, yeah. And you can see it even with these three names. Most of the squares on the screen are empty, like bytes and bits that are there and are allocated. And they need to be there because you need to be able to do that arithmetic thing of this being 0, this being 25. So you can jump from boom, 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 boom based on each of the letters. But it's a hugely sparse data structure, which means it takes up a crazy amount of memory. Now, maybe that's tolerable, especially for short names. But that's going to be the trade-off as well. And this is such a tension in computing. Almost any time you want to improve time, you want to speed up the efficiency, the speed of your algorithm, you're going to spend space. If, by contrast, you want to decrease the amount of space, you might very well have to increase the running time. It is indeed this seesaw back and forth. And you, your colleagues, your company need to decide what resource is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a human. Your time is valuable. Do you really want to spend hours implementing a try when, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource. And why sometimes there's good code or bad code, it depends on what you're prioritizing. So what do each of these nodes look like in a try? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26 that can point to more of these nodes. Notice that I don't need to store the name of someone in a try because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive cost. And what do we need our variable to be that stores the try? Just like before, we just need a single pointer that hangs on to the root of this structure that's null if it's empty, or non-null if it's actually pointing at something. Any questions then on tries? And if it's feeling like a lot, the fire hydrant, it is. We started with arrays, then linked lists, then tries. But questions on how we've just assembled from these basic building blocks? Yeah?
Why isn't the root of try have a size of 26? Why isn't that an array?
A good question. Why is this not size 26? It's just like with the try, just like with the linked list before. It just tends to be in code convenient to have a separate additional pointer that's small that just points to the beginning of the data structure, because that way it can be null, thereby clearly indicating there are no nodes, the whole structure is empty. If you allocated one of those nodes, you absolutely could, but then you'd be just wasting space even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. Other questions now on tries, or trees, or hash tables, or arrays? So what problems might arise? Well, here's a counterexample. What names are manifest in this try here? Feel free to just call it out. What do you see? Danielle and Daniel. So presumably, if these are two names here, one of which is a prefix of another, notice that the data structure still works. And I chose, a friend's name and then appended a couple of more characters to it that's also a name, because we have here D-A-N-I-E-L, and the green technically is implemented as a bool or something like that that indicates a word stops here. But we don't want to preclude storing Danielle as well, who's a superstring, if you will, of Daniel. And so that's OK too, so long as the structure allows for the pointers to keep going. So even that works out OK, whereas it might not have otherwise. And in terms of the running time, just to be clear, at the end of the day, tries do give you actual constant time for insertions, lookups, deletions, and the like, because it's dependent only on the length of the input, the key, if you will, and not on how many other people are in your phone or address book. And now thought we'd conclude with a visual. If you've gotten out into the square, anyone recognize this? OK, Sweetgreen, a local salad place. What are we looking at here, and what's its connection to today? You're about to become all the geekier in the real world, because you will start to see data structures everywhere. What is this? Or how does this work maybe in salad form? Who's been to Sweetgreen? OK, either of you. So how does this work? OK, good. So if you order a salad for someone named L, when it's ready, they put it in the L section here. And so this is kind of a set of key value pairs, right? If L is the first letter of someone's name, the value hopefully is the salad. And so what you kind of have here is a dictionary, key value pairs, where it's not words and definitions, it's names and salads. And you can think of this, too, as kind of a hash table. Why? Even though it actually doesn't fit on one long shelf, because the store is only so big, this is really an array. And apparently, A is missing, or maybe it's around the corner. But this array just happens to wrap onto multiple lines. But it's still conceptually a single dimension. But suppose two people have the name L. What do they do typically? Yeah, so maybe well, if they want to put that much effort into it, they might look at the second letter and then the third letter. Odds are this is not that interesting a problem to solve optimally in that way. But they probably do start stacking the salads on top of each other, or maybe scooching it over just a little bit. And so what do you have there? Well, now if you start to view the lens through like CS50 glasses, like, OK, you have an array, and then you have like these linked lists that are sort of growing here. But even then you run into a problem. Why? Because it's not really a linked list, because at some point you're going to hit the boundary here. So it's kind of like an array of arrays, because you can only fit, what, like 3 or 4 salads here. And so long story short, we started today deliberately talking about real world things like stacks and queues. And even though it did escalate quickly into binary search trees and hash tables and tries, even those things are everywhere, even though they don't call them as such. These are just solutions to problems. And now, with this final week of C under your belt, you have all the more of a technical toolkit by which to implement these things in code. Next week, we'll be able to trust that someone else solved all these problems. We'll introduce Python, and lines of code like this will finally become lines of code like that. So that's the promise ahead, and we'll see you next time.